Hi viewers, welcome to Sevivali Kalvi channel. Let us see the example for design a counter by using D flip-flops. So this is one of the gate questions which has already asked in previous years. So in this example, different sequences have given 0, 2, 3, 1, 0. So these are the different states which is given in this example. So by using this number of states, we are going to design the counter by using D flip-flops. So initial step, the given counter sequence must be correctly arranged in order 0, 2, 3, 1, 0. So in this order, the state transition is taken place for this example. So the number of states represented here are 4 states and the initial state is 0. So that can be denoted as S0. Normally we can represent the state by some variables or simply 0, 1, 2, 3. Likewise, the state values can be assigned. So if you want to mention as a state variable, we can take it as S0 for the state 0. Or simply if you want to represent 0 itself, no problem. We can represent that state by 0. And the second state also denoted as S2 in terms of variable, and state 3 represented by S3, state 1 represented by S1. So these are the different states already given in this question. After the state 1, again the transition goes to state 0. So that is represented here. So S0, S2, S1, and again S0 is the different state transition taken place in this example. So totally we have a 4 states and the corresponding states values can be assigned as in terms of 2 bits, that is 0, 0, 0, 1, 1, 0, 1, 1. So for 0 state, the corresponding 2 bits of values are 0, 0. For 2, 1, 0, 3, 1, 1, and for 1, 0, 1. So this is the states, and after the state S1 transition, it goes to state S0, that is initial condition, so 0, 0. So from this observation, we can draw the state diagram. So 0 state can be represented by 0, 0, 1 state 0, 1, 2 state 1, 0, 3 state 1, 1. And S0 is the initial state. The corresponding state values are 0, 0. So here 2-bit values are represented. So from this we can understand the 2 number of flip-flops are required for this corresponding example. That is 2 D flip-flops can be taken for this example to design a counter for this given sequence of states. So the initial state is S0 and the transition occurred from S0 to S2. That is next state for state S0 is S2. So the arrow indication move towards the S2. And from S2 to S3 transition is taken place. So S2 to S3, the arrow indication is mentioned here. And S3 to S1, the state transition happened. So S3 to S1 is happened, and after S1 again it moves to the initial condition S0. So the arrow indication mentioned like this. So 0, 0, 1, 0, 1, 1 and 0, 1. These are the different sequence of states transition is occurred in this example. So for the D flip-flop, this is the excitation table. So Qn, Qn plus 1, D, and Qn it may be 0 or 1. It is not a matter what input you are going to give in this D. That is, if you give 0, whether the Qn value is equal to 0 or 1, it's not a matter. What input is given in this flip-flop D, that will be the output, that is Qn plus 1, 0, 0. Similarly, the D Qn value is 0 or 1, it's not a matter. But what input you are going to give in this D, that is 1, that will be the output in this D flip-flop, that is Qn plus 1. So the D flip-flop does not consider the present state Qn, and it gives the output based on the given input to this D flip-flop. So this is excitation table. From this excitation table, we can make a transition table. So initially it consists of the present state. It is in the first column and the next state, and flip-flop inputs considered as a third column. So in this example, only two flip-flops can be taken because of 2 bits here. So because of this 2 bits, 2 flip-flops can be taken here. So the corresponding input for these two flip-flops are assigned as DA and DB because the flip-flop A input is DA and the flip-flop B input is assigned as DB. So the present state value QA and QB for first flip-flop and second flip-flop. Similarly, QA plus 1 and QP plus 1 is the next state for flip-flop A and flip-flop B. So from this we can arrange this sequence 0 0. So for initial condition the present state is 0 0. Now the transition occurred from 0 0 to 1 0. So 0 0 can be represented in first state and the next state value 1 0 and again next state value goes to 1 1, again next state value 0 1. So this can be arranged in this order. After that the 0 0 is the present state. When this condition is occurred, the next state for this present state is 1 0, that is S2 state. So the 0 0 corresponding next state is 1 0. This next state value move towards the next state here. Similarly, 1 0 is the present state at now. At the time, the next state will be 1 1. So the 1 0 corresponding present state, next state value will be 1 1. It moves towards next state here. Similarly, 1 1 is the present state now and the next state will be 0 1. So the 1 1 is the present state. The corresponding next state is 0 1. That is move from this position to next state here. And after that 0 1 is the present state and the corresponding next state transition is 0 0. So 0 1 can be represented in present state and the next state value will be 0 0 here. So this next state value move towards this next state column and we can fill the present state and the next state now. Now we can compare QA and QA plus 1. When the QA value 0, QA plus 1 value 1, our input is equal to 1. Because the excitation has, if the QN 0, QN plus 1, 1, the input is equal to 1. So based on this excitation table value, we can put here 1. Next QA 1 and QA plus 1, 1. The corresponding answer again 1. So the input value DA is again 1. Next QA1, QA plus 1, 0. So when this condition is taken, the D value is 0. So here we can put a 0. After that we can consider this 0, 1. So for this 0, 1 condition, again input, that is not consider this 0, 1. This 0 and this 0. When both are equal to 0, D value is equal to 0. Next, we have to move QB and QB plus 1 combination. So QB 0, QB plus 1 0, D will be 0 and QB 0, QB plus 1 1. So for this condition, this second case is considered. So the D value becomes 1 and QB is equal to 1, QB plus 1 equal to 1. Again, this condition is considered here. So the DB value becomes 1. And the last case QB 1 and QB plus 1 0. For 1 0 condition, DB value becomes 0. So this is the condition. So from this we have drawn the transition table. After that we have to make a K-map for simplification. And from this column DA and DB, we have to fill this value. So QA and QB are the present state. We have to consider here. So only 2 bits are considered. So we have to draw the 2 variable K-map. It consists of 2 rows and 2 columns, which has 4 cells. And we have to compare this 0 0 and the corresponding DA value will be 1. That is put it in the first cell. And 1 0 again DA value is 1 1 0 1. And after that for 1 1 0 and 0 1 also 0. So that values are put it in this corresponding cells and we can make this 2, 1 are in a single group. That is dual mapping can be done here, and the corresponding variable are to row value variable can be cancelled and the column only considered. So the for first column the corresponding value is binary 0. The corresponding variable is QB. If it is in SOP form 0, so the variable can be assigned as a bar. So Q bar is the answer for DA. Similarly for DB, we have to take this QA and QB. Whenever this both are equal to 0, DB value equal to 0, 1, 0, DB is equal to 1, 1, 1, again DB equal to 1, 0, 1, DB equal to 0. These all column values are put into this each and every cells. Finally, we can map this two ones are in a single group. So we can consider only second row. The two columns are alternate values, so it can be eliminated. So for this case, the second row is mapped. So the corresponding values are 1 and the variable is QA. So DB is equal to QA. So from this DA and DB Boolean expression, we can draw the counters logic diagram. So in this case, two flip-flops can be taken and assigned as flip-flop A and flip-flop B. Both are D flip-flop. So the corresponding inputs are DA and DB and outputs are QA, QB, QA bar, QB bar. And both two flip-flops are having the same clock pulse or synchronous clock pulse. So the clock pulse are joined together. At the same time, the DA answer is QB bar. So we directly take QB bar line and the QB bar output is given to the input for this DA. And similarly, DB is equal to QA. So the first flip-flop output is taken as an input for the second flip-flop. So directly this connection made here. So this is the design and implementation of counter by using D flip-flop for this particular given state transition condition. So for next example, the synchronous sequential circuit shown below works at a clock frequency of 1 gigahertz, the throughput in m bits per second and the latency in nanosecond respectively. So this is the given diagram. So it is also one of the gate question for previous years. So in this example, there are 3 D flip-flops are available. The inputs are assigned as D0, D1 and D2 and here input is given. The each and every flip-flop output is given to the input for next state of flip-flop. So the connection is serial in, serial out shift register concept and the clock signal is synchronous clock signal for all flip-flop. So the common clock frequency is given to every flip-flop. So from this observation, we have to analyze what is latency and what is throughput. We have to find out this value. So latency is nothing but time needed for an input change to produce an output change. That is simply we can express this latency as a length of time. So what is the length for the time? That is the input change to produce an output change. What is the time required for this changes can be denoted as a latency. So simply otherwise we can say in synchronous circuit as a certain number of clock cycles are to be represented. So this is latency definition. Similarly for throughput, the rate at which data can be processed. So how much amount of data can be processed at a particular time period or particular second. That is refers to the throughput. So in diagrammatic representation, we can differentiate this throughput and latency here. So in x-axis, we can take the time and y-axis, we can take traffic. So this is a throughput representation in graphical manner. So number of data packets arrived within a 1 second. So for 1 second, how many packets of data are arrived? That is the throughput. Similarly, for latency, also x-axis time parameter can be considered and in y-axis traffic can be considered and here time consumed for transfer of one packets. So here how many packets are transmitted or arrived within a second is denoted as throughput. Here, time consumption for transferring the one packet, which is called as a latency. So the latency can be determined with the formula small n into T clock, that is clock time period, where small n is the number of flip-flops. So in this example, there are 3 flip-flops are available. So from this observation, we denoted small n is equal to 3. So T clock can be defined with the help of frequency. So T is equal to inversely proportional to frequency. So T clock, which is equal to 1 divided by F clock. So in this example, F clock is given already. That is 1 gigahertz. So 1 gigahertz is 10 power 9 hertz. So 1 divided by 1 into 10 power 9. The final answer 10 power minus 9. That is 1 nanosecond is the clock time period. So from this throughput can be calculated. So throughput formula is number of bits per second. So 1 bit equal to 1 nanosecond. So throughput can be denoted as 10 power 9 bits per second. So simply 10 power 9 bits are transmitted uh, for this example. So 1000 megabits per second is the throughput answer for this question. So I think everyone understand this concept. So carefully calculate all the values by using this formula. And if you have any queries, you can put it in comments. Thank you all. Subscribe my channel, please. Thank you.